Greetings, my cosmic explorers. I'm Tobol, your guide to the mysteries of the universe. Welcome back to my blog, where science meets attitude and wonder knows no bounds. Today, we're diving into the mystery of the cosmic lightning. Few natural phenomena command attention like a jagged bolt tearing across the sky, illuminating the world in stark, brilliant white for a fleeting instant. How does this cosmic electricity form? Why does it strike where it does? To help us break it all down, I brought along the brilliant Brian. So grab your coffee, fasten your seatbelts, and get ready for some serious celestial wisdom. Brian, the floor is yours.
Thanks, May. I'll do my best to guide us through this thought-provoking topic. Let's explore the dreamscape together. Lightning. Few natural phenomena command attention like a jagged bolt tearing across the sky, illuminating the world in stark, brilliant white for a fleeting instant. It's a primal display of raw power, a reminder that our seemingly placid planet is constantly crackling with electrical energy. But beyond the awe-inspiring flash and the thunderous roar lies a web of mystery that has captivated humans for millennia. How does this cosmic electricity form? Why does it strike where it does? And what are those strange, ephemeral balls of light that sometimes follow in its wake? Let's delve into the electrifying world of lightning, uncovering both the known and the tantalizingly unknown. The story of lightning begins in the humble cumulonimbus cloud, that towering giant of the sky. But how does a fluffy-looking cloud transform into a factory of electrical chaos? The key lies in the cloud's turbulent interior. As warm, moist air rises, it cools and condenses, forming a churning mix of water droplets, ice crystals, and grapple, soft hail. It's within this chaotic dance that charges begin to separate. The exact mechanism is still debated, but collisions between these particles, driven by the violent updrafts and downdrafts, seem crucial. Lighter, positively charged ice crystals tend to be carried to the top of the cloud, while heavier, negatively charged graupel falls towards the middle or lower sections. This creates a massive capacitor in the sky, with positive charges at the top and negative charges building up below. But here's the cosmic twist. Getting this electrical engine started requires a spark, and surprisingly, that spark often comes from outer space. Galactic cosmic rays, high-energy particles hurtling towards Earth from distant stellar explosions, bombard our atmosphere. When they reach the lower regions of a thundercloud, they can ionize air molecules, creating the initial electrons needed to trigger the avalanche of electrical breakdown we call lightning. Without these cosmic messengers, the powerful electric fields within the cloud might never reach the critical point for a discharge. As some scientists note, it's as if lightning couldn't happen in clouds without cosmic rays. These thunderclouds are not just puffy masses of water vapor, they are colossal electrical storage units. The charge separation can create enormous potential differences. While the exact potential inside a cloud is hard to measure directly, estimates suggest differences of hundreds of millions of volts, megavolts, between the positively charged top and the negatively charged base. The electric field strength can reach up to 3,000 volts per centimeter in some regions, a field strong enough to initiate the complex process leading to a lightning strike. This immense electrical tension is the driving force behind one of nature's most dramatic displays. Contrary to popular belief, the majority of lightning activity occurs within the clouds themselves or between different clouds. Only about 25% of lightning discharges actually reach the ground. This intra-cloud, IC, and cloud-to-cloud, CC lightning is a constant hidden battle of electrical forces high in the atmosphere, often illuminating the cloud's interior with spectacular sheet lightning or the branching tendrils of heat lightning seen on the horizon. While we often think of lightning as descending from the heavens, a significant part of the process involves an upward journey. When the negatively charged region of a cloud approaches the ground, it induces a positive charge on the Earth's surface below. As the electric field intensifies near tall objects like trees, buildings, or mountains, it can initiate an upward-moving leader, a channel of ionized air reaching towards the cloud. When this upward leader meets the downward leader from the cloud, the main lightning strike occurs, often traveling up the established channel. This is why lightning rods work. They provide a preferred path for this upward leader. Throughout history, lightning strikes on religious buildings have been seen as divine intervention. While the theological implications are left to philosophers and theologians, the physical reason is purely architectural. Churches and temples, often built on high ground or designed to be the tallest structures in an area, act as natural lightning rods. Their height makes them prime targets for the electrical discharge, seeking the easiest path to the ground. Add a lightning rod, often installed later, ironically, and the target becomes even more inviting. While the conditions for lightning formation are governed by physics, the actual strike point exhibits a strong element of randomness. The path a lightning bolt takes is influenced by the constantly shifting distribution of electrical charges, air density, humidity, and even dust particles. However, this randomness is not absolute. Tall, pointed objects significantly increase the probability of a strike. As some scientists explain, the trajectory is rather random, but the likelihood of hitting a specific location is heavily influenced by its electrical environment and physical prominence. This preference for height is one of the few certainties in the world of lightning. The taller an object, the more it distorts the electric field around it, making it easier for the initial leader to start. For example, the iconic Ostankino Tower in Moscow, at 540 meters tall, is struck by lightning around 30 times per year, far more frequently than the surrounding area. It's not just about height. It's about creating a localized hotspot for electrical discharge. Do lightning bolts move towards each other? Absolutely. The process is a two-way dance. A step leader moves downwards from the cloud in a series of jumps, while an upward leader, or streamer, rises from the ground or a tall object. When these two leaders meet, usually hundreds of meters above the surface, a conductive channel is established. The main return stroke then surges up this channel from the ground, producing the brilliant flash we see. It's a cosmic meet-cute, albeit a very hot and fast one. How long does a lightning bolt last? Despite its tremendous power, a lightning strike is incredibly brief. The entire visible process, from the initial leader to the final return stroke, typically lasts only about 0.2 seconds. However, what we often perceive as a single flash is usually a series of strokes. The main return stroke is followed by several subsequent strokes, each separated by roughly 30–60 milliseconds. This rapid succession is why lightning sometimes appears to flicker. Does lightning strike more than once? Yes, and quite frequently. A single lightning flash can consist of multiple strokes, often ranging from 2 to 20 or more. These multiple strokes travel along the same ionized channel, which is why you might see a flickering effect. This multi-stroke nature is part of what gives lightning its complex, branching appearance. But what is the energy of a lightning strike? The energy contained in a single lightning bolt is staggering. A typical strike carries a charge of tens of coulombs and a potential difference of hundreds of millions of volts. The total energy released can be equivalent to a small explosive device, though concentrated into an incredibly short time. This immense, albeit brief power is what makes lightning so destructive, capable of splitting trees, damaging buildings, and posing a serious threat to life. Why does lightning cause damage? The destruction wrought by lightning is primarily due to three factors: the sheer electrical current, often tens of thousands of amperes, the extreme heat generated along the channel, reaching temperatures of around 30,000 Kelvin or 5 times hotter than the sun's surface, and the explosive expansion of air caused by this rapid heating. This expansion creates the thunderclap and generates powerful shock waves that can shatter objects nearby. If lightning requires the right conditions, an atmosphere, turbulence, and charge separation, could it happen elsewhere in the solar system? Venus. The question of lightning on Venus is surprisingly contentious. Early Soviet missions detected signals that could be interpreted as lightning, but the planet's thick, hot atmosphere and lack of significant water vapor make conventional cloud electrification seem unlikely. Yet, Recent infrared observations hint at possible volcanic activity which could generate electrical discharges. As some scientists note, the question of lightning on Venus is almost as fundamental as the question of life on Mars. It remains an open puzzle. Jupiter and Saturn. On these gas giants, lightning is a confirmed and spectacular phenomenon. The giant storms, like Jupiter's Great Red Spot, host lightning bolts that can be hundreds of times more powerful than those on Earth, illuminating vast regions of the planet's cloudy atmosphere. Do volcanoes generate lightning? Volcanic eruptions create their own electrical storms. The towering ash plumes, filled with rapidly moving particles of rock, dust and gas, generate intense turbulence and charge separation. The result? Spectacular lightning displays within the volcanic cloud, sometimes producing kilometer-long bolts. These dirty thunderstorms are a dramatic reminder of the raw forces at play during an eruption. On Earth we hear thunder, but what about Venus? The dense atmosphere would muffle sound waves significantly. However, the electrical discharges associated with potential Venusian lightning would still generate electromagnetic waves. Scientists have used radio instruments on spacecraft to listen for these signatures, searching for the electromagnetic crackle that would betray the presence of lightning in the sulfuric acid clouds above the scorching surface. The link between cosmic rays and lightning adds a fascinating layer to the story. These high-energy particles, originating from supernovae and other violent cosmic events, provide the initial spark needed to trigger the electrical breakdown in thunderclouds. Without this cosmic input, the natural electric fields in clouds might never become strong enough to initiate a lightning strike. We are literally witnessing the influence of the wider universe on our local weather. Meteor trails, the glowing streaks left by space rocks burning up in the atmosphere, create temporary columns of ionized gas. While it's an intriguing idea, scientists indicate that lightning typically doesn't preferentially strike these channels. The turbulent, charged environment of a thundercloud is far more conducive to lightning initiation than a thin, linear ionization trail. What are St. Elmo's fires? Those eerie blue-purple glows sometimes seen on ship masts, airplane wings, or church spires during storms are known as St. Elmo's fires. Far from being lightning itself, they are a type of corona discharge, a continuous electrical glow that occurs when the electric field around a pointed conductor becomes strong enough to ionize the surrounding air, but not strong enough to create a full spark or lightning bolt. It's nature's own neon sign, often appearing as a dancing, finger-like flame. During a storm, power lines can emit a crackling or humming sound. This is caused by corona discharge occurring along the line's surface, especially at points or damaged areas. Water droplets increase the local electric field strength, making it easier for small electrical arcs or streamers to form. These tiny discharges create the characteristic crackling sound, a miniature version of the larger forces at play in a lightning strike. Believe it or not, corona discharge has found its way into beauty treatments. Devices based on corona discharge principles, like the D'Arsonval apparatus, use tiny electrical currents to stimulate the skin. While not actual lightning, these devices use the same fundamental physics of electrical discharge in air to achieve their effects, albeit at much lower energies. While lightning strikes occur over both land and sea, the frequency per square kilometer is generally higher over land. This is largely due to the greater frequency of convective thunderstorms over heated land masses compared to the more stable air masses over large bodies of water. However, intense weather systems moving over warm seas like the Mediterranean can generate significant lightning activity, especially during winter storms when cold air masses collide with the relatively warm water. Ships, especially large ones, are vulnerable to lightning strikes. Being tall, conductive objects surrounded by a conductive medium, salt water, they provide a clear path for electrical discharge. However, modern ships are equipped with lightning protection systems, including grounding conductors, to safely channel the electrical current into the water and minimize damage or risk to crew. Airplanes are frequent flyers through thunderclouds and encounter strong electrical fields. However, they are designed with this in mind. The aircraft's metal skin acts as a Faraday cage, protecting the interior. When lightning strikes an airplane, the The current typically flows along the outside of the fuselage and wings, exiting through another point, usually a wingtip or the tail. While strikes can cause minor damage to avionics or the exterior, modern aircraft are built to withstand them, making air travel remarkably safe even during electrical storms. Ball lightning is one of the most enduring mysteries in atmospheric physics. Described as glowing, spherical objects, often the size of a grapefruit, that drift slowly, sometimes through solid objects like walls or windows, before disappearing or exploding. For years, many scientists doubted its existence, attributing reports to optical illusions or hallucinations. However, reliable eyewitness accounts from credible sources, including scientists and even a few video recordings, have convinced the scientific community that ball lightning is a real, albeit rare, physical phenomenon. Its mechanism of formation and sustenance remains completely unknown. Ordinary lightning lasts microseconds. Ball lightning, however, reportedly persists for seconds, sometimes even tens of seconds, an extraordinarily long time for such a high-energy electrical discharge in air. This longevity is its greatest mystery. Conventional physics struggles to explain how a ball of plasma could remain stable and contained for so long without an obvious energy source. Various theories exist, from exotic chemical reactions to microwave cavities, but none have gained universal acceptance. Can you direct lightning with a rocket? Incredibly, yes. Scientists have developed techniques to trigger lightning using small rockets. A rocket is launched into a thundercloud carrying a thin, grounded wire. As the rocket ascends, it creates a temporary conductive path. This path can initiate an upward leader, which can then connect with the downward leader from the cloud, triggering a lightning strike along the wire's path. This method allows researchers to study lightning up close in a controlled, though still extremely dangerous manner. Ball lightning seems to occur most frequently during thunderstorms, often appearing in the aftermath of a regular lightning strike, sometimes entering buildings through windows or doors. Its appearance appears to be somewhat random and extremely rare to witness. Lightning doesn't just strike downwards or horizontally. Some discharges escape upwards, reaching into the upper atmosphere and even space. These include sprites. These are large red jellyfish-like electrical discharges that occur high above thunderstorms, typically at altitudes of 50 to 90 kilometers. They are triggered by positive cloud-to-ground lightning and were only confirmed by scientists in the late 20th century, despite being reported by pilots for decades. Elves, brief disc-shaped glows that appear at the edge of space around 90 to 100 kilometers altitude, caused by the electromagnetic pulse from a lightning strike below. Blue jets, cone-shaped discharges that shoot upwards from the tops of thunderclouds into the stratosphere, reaching altitudes of up to 40 to 50 kilometers. These phenomena represent the upper atmospheric extension of the thunderstorm's electrical activity, a hidden world of electrical fireworks above the clouds. Historical nuclear tests provided a unique, albeit disturbing, laboratory for studying atmospheric electricity. The massive electromagnetic pulses and atmospheric disturbances created by these explosions were observed to influence weather patterns, including potentially increasing lightning activity. While such experiments are thankfully a thing of the past, they highlighted the complex interconnections between large-scale energy releases and atmospheric electrical phenomena. Can you hear lightning on the radio? Absolutely. Lightning is a powerful source of radio waves. Anyone tuning a simple AM radio during a thunderstorm can often hear the sharp crackling sounds of nearby strikes. These sounds are caused by the intense electromagnetic pulse generated by the lightning discharge. Different radio frequencies pick up different aspects of the lightning's electromagnetic signature, offering a unique way to listen to the storm's electrical activity. What don't we know about lightning? Despite centuries of observation and decades of scientific study, lightning still holds profound secrets. The fundamental question, the precise mechanism by which a lightning bolt initiates within a cloud, remains hotly debated. How do the relatively weak electric fields measured in clouds overcome air's natural insulation to create the initial spark, especially when cosmic rays are only part of the story? The role of turbulence, the exact dynamics of charge generation and separation, and the initiation of leaders are all active areas of research. As some scientists emphasize, understanding how lightning is born is the hottest topic in lightning physics right now. Perhaps most intriguingly, integrating lightning into global weather and climate models remains a challenge. Lightning is not just a dramatic display, it plays a role in atmospheric chemistry, influencing the production of nitrogen oxides and may be an indicator of broader atmospheric turbulence. Fully understanding and modeling its impact is crucial for improving weather forecasting and climate science. Lightning is a cosmic dance between Earth's atmosphere and the wider universe, a fleeting yet powerful reminder of the dynamic forces that shape our world. From the initial cosmic spark to the final flicker of ball lightning, it remains one of nature's most captivating and least understood phenomena. As we continue to probe its mysteries, one thing is certain: lightning will continue to electrify our skies and our imaginations for generations to come. So the next time you see a storm brewing, don't just seek shelter, marvel at the incredible invisible forces at play, and remember you're witnessing a small piece of the universe's grand electrical symphony. Just maybe keep the radio on to hear the thunder's song.
And there you have it, my cosmic companions. Remember, every challenge is just a stepping stone to greatness. If you enjoyed this episode, don't forget to hit that like button, subscribe so we can keep exploring together, and drop a comment to share your thoughts. Until next time, stay curious, stay bold, and keep chasing those dreams.